far we were discussing about cruise, climb, landing. Now let us talk about how to trim aircraft for maneuver. We'll take two cases. One is pull-up, another is steady coordinated turn. We'll be discussing how to trim an aircraft for maneuver. One is pull-up and another is steady coordinated turn, right? What is a pull-up? This is the airplane. This is V. We have to generate lift, W, and this is the thrust, this is the drag. And you know, if you want to go for this radius R, then lift has to be greater than W. So L minus W is equal to M V square upon R. We are all familiar with this because this difference in lift and weight is only giving centripetal acceleration, and which is modeled through mv square upon r. And we know L is equal to NW, or in a sense we say N is L by W, that is called load factor. Right? You are advised to read my first course on Introduction to Performance if you want to know more about these things, but I'll just glance through this so that there's a continuity. So now from this relationship what I get, NW minus W is equal to M V into V by R, or W N minus 1 is equal to M V into Q. V by R is what? Is the pitch rate. Okay? This is the V and this is radius R. So what is the angular rate? That is Q. So this angular rate is about, remember, about y-axis. Correct? So now I have replaced V by R by Q, and I can write this mg n minus 1 is equal to m V into Q. Gets cancelled, so I get Q for pull-up is G by V n minus 1. What is the meaning of this? If I plan to go for a load factor of n at a particular speed v, then the pitch rate will be q given by this relationship. Right? So if I want to go for a same load factor at a lower speed, then the q should be higher. And you have to generate this q. Who generates this q? It is through the elevator. Okay? This is one for pull-up. Similarly, if I come for steady coordinated turn, this is lift, this is W, and this is your y-axis, this is your z-axis. Y, Z are body fixed axis, so if the airplane has banged by phi, so body fixed axis is also tilted by this. For example, this is the airplane, and let's say this is the z-axis, this is the body fixed axis. So if the airplane bangs, the z-axis also rotates. That is how you are seeing this z-axis, right? Similarly, y-axis. If this is true, it is taking a turn about with a psi dot about a fixed vertical axis z earth axis I say, rotating through about that axis, and that notation is psi dot, turn rate is psi dot. So it is something like this. It is banking like this and turning like this. Okay? Okay? So this is the definition of psi dot. Now if I write the equation, I find if it is coordinated, that we should not also lose the height. So this is L cos of phi. So I must have L cos of phi equal to W. So the L cos phi component of lift should balance the weight, and L sin phi component must be equal to mv square upon r, because this L sin phi component, because it has two components, one this and one this, is the L sin phi component. That is going to give you L sin phi, if I write it here, that is responsible to give you centripetal acceleration, right? So this is equal to mv square upon r. So I can write tan phi equal to v square upon rg. This is straightforward, dividing this by this. And we also know psi dot equal to v by r. That is true. Let me write few expressions so that we don't get lost unnecessarily. So psi dot equal to v by r. What is q? Will there be any q in this? See, one thing you understand, if the airplane is like this and taking a turn like this, then there should not be any q. That is local y-axis, local body y-axis. But if the airplane is banked like this, then it is turning like this, then there will come a component about local y-axis, which is along the span of the airplane. You can see that this is y-axis, and this is the psi dot. So if I draw a psi dot here parallelly, then there will be a component along y-axis, and that is equal to psi dot sine phi. You see this? This, one component will come here, and that is nothing but this is phi, this angle is 90, this is again phi. You can find out yourself, this is phi, 90 minus phi. So this is 90 minus phi. The cos component will become sine component, because cos 90 minus phi is sine phi. So q equal to psi dot sine phi. However, physically also you could see, if I'm turning like this, there is no motion of like this. But if I'm banked like this, and my y-axis is this one, now if I turn, I'm actually turning about y-axis also. That is, if you could check it, if phi is 0, then there won't be any pitch rate because of psi dot. But if there is a phi, there will be q because of phi, because of psi dot. Okay? We now will substitute few expression and try to get q for steady coordinate turn in terms of load factor and velocity. So we'll do some manipulation. We have seen that tan phi equal to v square by rg, or r equal to v square by g tan phi, right? This is what we have derived. Now what is q? Q is psi dot sine phi. And what is psi dot? Psi dot is v by r sine phi. Okay? This part we have come. After that, q equal to v by r sine phi, and r equal to v square by g tan phi. So if I put r here, I should get expression. If I put r here, please do yourself r here, then I will get q is equal to g by v sine phi tan phi. So q equal to g by v sine phi tan phi, and sine phi is what? Cos, and tan phi is what? If I know this, I can put it here, I will get the expression for q. One thing I know, that L cos phi is equal to W, or L by W is equal to 1 by cos phi. This is equal to N, called the load factor. No objection? You know that L cos phi was balancing the weight, so L by W will be 1 by cos phi, and L by W is nothing but load factor, so I can write load factor equal to 1 by cos phi. What is the meaning of that? If you are turning and not losing your height, altitude, then you can easily find out what is the load factor by just taking 1 by cos phi as a computation. Okay? So now what? What is our aim? Our aim is to see here. It's very straightforward. Cos phi, you know, 1 by n. So you can show that sine phi is equal to under root n square minus 1 by n, and you can show tan phi is equal to under root n square minus 1. So if I put all this thing here, then I will get Q for, I write here, Q for steady coordinate turn as G by V n minus 1 by n. Let me repeat, this is a little bit of algebraic manipulation, and I will always suggest you do yourself. But let me repeat for your clarity. Q is psi dot sine phi, this you have understood. Tan phi, V square by Rg already you have seen. So R is this. So in Q psi dot sine phi is nothing but V by R, so I put V by R here, and sine phi is here. For R, we substitute this expression to get Q as G by V sine phi and tan phi. We wanted to find sine phi and tan phi, what are their expressions. We know L cos phi equal to W, so we know n equal to 1 by cos phi. So cos phi equal to 1 by n. So you can find sine phi and tan phi, substitute there, and you'll get expression this. So what is the meaning of this? Then let me erase this, all this term. Once again I repeat, if you have any difficulty, please read my first course, MOOCs lecture, you will get, or any standard textbook you take. Now we are coming back to the control part of it. What sort of an elevated deflection we should give. Before we decide what sort of elevated deflection we should give, let us again relook. What are this? What is this Q pull-up? What does it say? If I want to go for a load factor of n, pull up like this, then I need to generate this much of Q. And it says if I want to go for a steady coordinate turn for a given load factor n, then I need to generate Q given by this expression at a particular speed. And also realize that if the speed is lower, then the Q will increase. But you also know that there's a limit on V, it cannot be less than V stall. Okay, now what is the question? So what is the delta E required for pull-up? For pull-up with load factor N. Right? So this is important. Please understand what I am going to say now. We are looking for delta E required for pull-up with load factor N. What is the pull-up? The airplane is going, remember this is the fuselage, assume there is a wing, and this is the tail. Right, okay? White part is the tail. So I'm going in a cruise, then I have to pull up means I have to generate a Q, so I will do like this. The moment I'm giving a Q, and this Q is proportional to whatever load factor I want. So once I'm giving a Q, what is happening? This tail is going downward, about CG, going downward. So it will be seeing induced air component which are like Q, LT, right? This is the induced V. Relative airspeed, right? This is going Q up, it is going down. LT is the distance between CG and the AC of the tail. Right? So if I draw it, this is the tail, this is the AC of the tail, and this is the CG. It is going for a Q like this, so it is going down like this. So there is a relative air speed, which is Q into LT, where LT is the tail moment arm, we know that, and this is Q. So you could see from here, if this airplane is going for a pitch rate Q, then this tail is going downward like this. So there will be relative air QLT, that is V equal to omega R, right? That will be seen at the AC of the wing. So, and this airplane is also moving forward. So delta alpha tail will be QLT by V. This much of additional angle of attack will be seen by the tail when the airplane is doing a pull-up like this. That is when there is a Q. And the moment delta alpha T, which is now more than the alpha seen during cruise, because he was cruising like this, then he was doing the pull-up. So I have to again put additional elevator so that this delta alpha T, which will cause a nose-down moment, is now taken care, right? So I have to give more delta. That is, this delta alpha T will give some delta L, and that will give some delta M. So if I want to trim at that Q, I must ensure that this additional delta M should be corrected by elevator deflection, over and above whatever delta E was there for cruise. This part is clear? I repeat again. When I am cruising, I have put some delta E, elevator deflection. Now I am pulling up. The moment I try to pull up, then I see additional angle coming at the tail. So that additional angle at the tail will give me a nose down moment. I don't want that. I have to counter it. So I have to give the elevator deflection a little more up, so that I counter whatever change of delta alpha t is there. So that will be my new delta E required for a pull-up. One thing you can understand, I can say that in a pull-up, since there is an additional moment, nose down moment is coming, which is trying to oppose it, so I say so it is apparently increasing its stability. Okay? That is why I need to give additional elevator deflection, because it has become, in the process, it has become more stable, right? So now how do I find what is the delta E additional required? If this is clear, then the job is simple. I know that what is tau? Tau is d alpha t by d delta E. So I can write tau into d delta E, additional delta E required to change alpha t by how much amount? By q Lt by v. So if they balances, so I put equal to 0, so I get delta E equal to minus q Lt by tau into v. This is the additional delta E up required for a positive q. But generally what happens, we have considered only tail. If it is customary, you multiply by 1.1 to take care of wing fuselage, which are ahead of the wing, or wing fuselage combination. It's a typical number, around 10% you can add, right? Okay. So what is the method now? It should be very straightforward to you. What we have got? The delta E required to trim at maneuver is minus 1.1 q Lt by tau v. I repeat, delta E required, the additional elevator deflection required for a pull-up by q is minus 1.1 Lt q tau v, right? So what was during cruise? It was delta E naught plus d delta E by dCl trim into CL trim, right? Now what will happen? Because of this q, I have to add this also. Right? This is clear? So this is the additional thing you have to add to whatever you are in the cruise. Whatever elevator deflection of a cruise, the moment we want to go for a pull-up, I have to calculate what is the value of q, and with this expression, I must give additional delta E to trim for that pull-up maneuver. This is the understanding. Okay? So if I ask you a question, if I am going for a pull-up, then what q I should use? For pull-up, I should use this q. If I am going for a steady coordinated turn, which q I should use? I should use this q. That's all, as simple as that. That answers the question, how much delta E required to trim the airplane for a particular pull-up or particular steady coordinated turn, right? For a given load factor n, correct? So delta E, we are trying to find out what will be delta E for pull-up. We know that delta E is given by minus q Lt by tau v and into 1.1. We agreed for giving some consideration for fuselage and wing, etc. So then I should know this equal to minus 1.1 Lt by tau v, and for pull-up I will pick up the expression of q for pull-up, and that is g by v into n minus 1. So effectively it becomes minus 1.1 g by tau v square Lt into n minus 1. This is the delta E required for pull-up, meaning thereby for a given velocity, if you are going for a pull-up, over and above your cruise delta E, I have to give this much of elevator deflection up. So similarly, for delta delta E for a steady coordinate turn will be again minus 1.1. Now for Q, I should take the expression for steady coordinate turn, which is n minus 1 by n. So minus 1.1 into Q into LT divided by tau into V. So what is the expression then becomes? So delta delta E for SCT equal to minus 1.1 G LT by tau V square into n minus 1 by n. What was for pull-up? It was minus 1.1 G by tau V square LT into n minus 1. But here it is minus 1 G LT by tau V square n minus 1 by n. That is the difference. So let me write it neatly as the final result because we'll be using it in our next class. I repeat, all of you please derive this yourself. Unless you derive this yourself, pen and pencil, it will not go to your mind. So what we have derived is delta delta E for pull-up is given by minus 1.1 G LT by tau V square into n minus 1, and delta delta E for a steady coordinate turn as minus 1.1 G LT by tau V square into n minus 1 by n. So what happens if I am trying to find out how much delta E I have to give for a pull-up total? One part will be because of cruise, which is already there, delta E naught plus d delta E by dCl into Cl. Now it will come minus 1.1 G LT by tau V square n minus 1. And what is the Cl here? Cl is nothing but NW by half rho V square S, because L equal to NW, so Cl will be NW by half rho V square S. This is for pull-up. Okay, similarly delta E for steady coordinate turn, already equilibrium screws, that much delta was required by dCl into Cl, where Cl is again NW by half rho V square S, and then minus 1.1 GLT by tau V square n minus 1 by n. This is our final findings. So I block it here, focus here. Let us come back here. So if n is equal to 1, that is just cruising, lift equal to weight, how much delta E required? Then required delta E naught or d delta by dCl into Cl trim. Cl trim is nothing but Cl cruise with n equal to 1. Right? But as n is increased, then our delta E has more negative component from here. That is, you have to put elevator up and up. Similarly, true here for steady coordinate turn. Right? The difference is coming only because the Q are different. One is G by V n minus 1, another is G by V n minus 1 by n. Right? But one thing you could see loosely as a designer, if n is very large, then n minus 1 becomes n, and n minus 1 by n also becomes n, or approaches n. So that time the Q, both the Q's are same, right? And as n increases, then the Q remains same. So delta E required additional will be, or delta complete required will be almost same, right? That's what you should know that a priori. From here, next lecture we'll try to find out what is that CG location at which d delta E by dN goes to 0, because Cl, for Cl I put n here, here n is there. If I find this gradient, that is d delta E by dN, d delta E by dN, that is for different load factor, how much, what is the gradient of delta E in terms of load factor increase or decrease. That derivation we'll find out, and we'll see something very interesting. We'll find there is a CG location at which d delta E by dN becomes 0, and that will define it as stick-fixed maneuvering point.